In this lab, we apply the momentum principle, Newton's second law, and also the energy principle for the analysis of a spring with an attached mass. Using the software tracker, we set up the calibration length and also the reference axis. The movement of the system was manually tracked frame by frame. The X and Y positions were collected in a CSV file. Here we have the tracking of the movement, the X and Y axis. Considering Newton's second law and also the momentum and also the energy principle, we constructed a computational model. The mass of the object and the stiffness of the spring and the relaxed length of the spring were obtained from the lecture Rope Physics, since here we use the same system. It's important to note that we had to introduce an adjustment to the length of the spring. We tracked the center of the object, but this does not correspond to the spring length. There's a difference of 5.7 centimeters. We had to take this into account to obtain a better agreement between the model and the experiment. We considered the force actuating the system and we obtained the net force, updated the velocity and also the position. After that, we updated the length of the spring. Running this code, we obtained these figures. We can see that there's a very good agreement in the beginning of the movement, and this agreement becomes poorer during the time. The main causes are we do not consider the dissipation of energy and also errors in the measurement. In the code loop, we also analyzed the energy principle. We considered the kinetic energy, the potential gravitational energy and the spring energy. We calculated these quantities and also their variation, the deltas. Running the code, we observe the flow of energy. And we also note that delta E is equal to 0. In the graph we had delta K in red, delta UG, in green, delta US, and yellow, delta E. The proposed questions were: is the energy principle satisfied? Yes, although we should remember that we do not consider the dissipation energy. We also used data from tracker to estimate the period of oscillation. Using data from the x-axis, we obtained 1.64 seconds, and using the y data, 1.52 seconds. There is a difference of 8%. Thank you.